In this video, I want to talk about resistors in series, that is, resistors that are connected as shown in the diagram. Basically, the idea is that the current that flows through the first resistance, in this case R1, is the same current that flows through the resistance R2. So let's just think about how the current flow is going to happen in this circuit. So at this point here, we have a voltage source, and I've drawn a slightly different symbol than I introduced to you before. So here the voltage source is denoted by this symbol. And basically this longer line is the positive side of the voltage supply, where the shorter line is the negative side of the voltage supply. Okay. So here's the voltage source, and the current flows out of the positive terminal. It goes through this wire, flows into the resistor, and the same current that is flowing through resistance R1 also flows through resistance R2. And it has to, because there is no place for the current to either drop off the circuit, because there's no other path for the current to flow. Neither is there anything here that is going to store the current and keep the charge, right? So the current has to be the same, and it flows through R2, through this wire, back into the power supply. Okay, so the same current I, let's call it, flows through the resistance R1, and it also flows through the resistance R2. Now notice, I'm not saying the same value of the current, I'm saying the same current. It is exactly the current that is going in here, which is also going to go into R2. And therefore, these two resistors are called, we call them, and we say that they are in series. Okay. So we've looked at the current, how it flows. Now let's just think about the voltage. Okay. So if we want to find what the value of this current is, we need to think about what voltages are being applied across the resistors. Okay, so let's just mark points. Let's call this point A in our circuit. Let's call this point B, and let's call this point C. Okay, so if we know the voltage at point A and B, we know the voltage that is across R1. And if we know the voltage at point C as well, the potential at point C as well, then we know the voltage that is being applied across R2 as well. Is that right? Okay. Now, what is the potential at point A? Now, we can see that there is a wire being connected from point A to the voltage source. And this wire is basically a symbol of an equipotential line. That is a line that connects 2 points which have the same potential. Okay. So this voltage, this entire voltage that I'm trying to draw in red is the same potential. And the potential is V with respect to this point. Let me draw it in a different color. This point, which has the same potential as point C, which is one end of resistance R2, right? So let's just think about the potentials now. So we know that the voltage between point A and point C is V. Okay. We, however, what we don't know is what the potential at point B is. Okay. So let's say, let's say that the voltage between point A and B, the difference between A and B, the voltage difference here, or in other words, the voltage that is applied across R1 is V1. And let's say the voltage that is applied across R2 is V2. So what I'm saying is VA, so the potential at point A here, minus VB equal to V1. And similarly, I'm saying VB minus VC equal to V2. Okay, but we also know that the potential difference between point A and point C, which can be written as VA minus VC, is equal to V. Now if you look at these three equations, you would easily see that if you add these two equations, you get VA minus VC equal to V1 plus V2. So, and then comparing the addition of this equation with this equation, what we basically get is that V is equal to V1 plus V2. So what we are saying is that the potential across this resistance R1 and the potential across this resistance R2 add up to give the total potential across both the resistances. Okay, so let me just clean up the slide a bit and then we can continue. Okay, so we have worked out that the total potential between point A and C is the sum of the potentials between resistance R1 and resistance R2. Okay, but we can go beyond this, right? So what is V1? So this V1 is the voltage across the resistance R1. And how is the voltage across the resistance R1 related to I? Remember from the equations that we wrote last time, and this equation is also called the Ohm's law. What we say is this voltage is I times R1. And similarly, the voltage across V2 is the current times the resistance R2, which is I R2. Okay, and therefore we can write V over I is equal to R1 plus R2. In other words, if you could kind of combine this entire system, this connection of these two resistance R1 and R2, and make it like one resistance. Okay, so if let's say you could draw a circuit, you could try to replace this entire thing with this big mega resistor, and if this resistance had a value of R1 plus R2, and let's call it the equivalent resistance R1 plus R2, then this resistor would generate exactly the same amount of current that the combination of R1 and R2 were doing. So in other words, when two resistors are connected in series, they act as one resistor which has a resistance that is equal to the sum of the resistances of the individual resistors. Now, that is not to say that we get all the information in the circuit by doing that. Now, let's just take away this this combined resistance. If we have that combined resistance, we know what the current is, right? So we know what the current is and we know what the voltage is, but we don't know how the voltage is divided between the two resistances, right? So as far as the external circuit is concerned, so if we divide the circuit into two parts, one which is this side to the left of the resistor network, we can combine the resistances. But if we want to know the internal behavior of these resistances, then we have to look at this resistances separately, and we can't just combine them because we would not know the internals. Okay, having looked at all that, let's just think about how these resistances actually give you voltage division, which is what they do. Okay, so we already wrote in the previous slide that V over I is equal to R1 plus R2, and that of course can be written as the current. Let's just evaluate the current. So I is equal to V over R1 plus R2. Okay, so what is the voltage V1? V1 is going to be I times R1, because I is the current that flows through this resistance, and the resistance of the resistor is R1. So V1 is I times R1. Okay, and you can substitute the value of I from here. So what do you get? So what we get is this is equal to V times R1 by R1 plus R2. Similarly, if you look at the voltage V2, what you'll get is V times R2 by R1 plus R2. And so what we can see is that this voltage V, by using two resistors in series, we can divide this voltage into two parts. And basically it acts as a voltage divider. One is V1 and another is V2. And this voltage division happens in the ratio of the resistors that we have connected, right? So let's summarize what we have learned with these resistors in series. So point number one, we say resistors are in series. What's the definition for when they are in series? When the currents are the same, or the same current is flowing through both the resistors. And I said that when we are saying same current, we do not mean just that the value of the currents are the same, but that exactly the same current, the current that is flowing through R1 also flows through the other resistance. We also saw that if two resistors are in series, their equivalent resistance is given by their sum, R1 plus R2. And we saw that the voltage across each resistance is proportional to the resistance. So V1 is equal to R1 over R1 plus R2 times the total voltage across the two resistors. Okay, so that's resistance in series. And what we see is that resistors in series can perform voltage division for us. Let me just conclude by looking at a simple application, an application that we described earlier as well in one of the videos. So think about a voltage source here, and this is connected to two resistances. So this resistance R1 is a fixed resistor, and there's another resistance here, and this is basically a sensor whose resistance changes in accordance with a particular physical parameter. Let's say the resistance is in some way related to the temperature. Okay, and what we are recording as the output of this circuit is this voltage. Let's call it V sensor. Now, from our analysis previously, if the voltage is V, the V sensor, so V sensor is going to be equal to V times R sensor over R plus R sensor. Okay, and if this R1, if we assume that R1 is much greater than R sensor, then what we can do is we can write that this is approximately R sensor over R. which means that this voltage or the voltage or output of this circuit is proportional to the resistance of the sensor. And this resistance is somehow related to, if we are using a temperature sensor, to the temperature. And therefore, this voltage is related to the temperature. And that's how many sensors work. And that's one application of voltage division.